Welcome to my YouTube channel PCM Academy and myself Prasenjit Mallik, M.sc in Physics. We are in a lecture series of IIT JAM Mathematical Physics, and we have completed many topics of mathematical physics like single and multivariable calculus, vector calculus, Fourier series, differential equation, and now we are going to start a new topic, that is matrices. And if you are new in this channel, then please subscribe my channel and also go to the description to join the Telegram channel, so you can get the PDF notes of the topics that I have discussed here. Okay, so today we will start a new topic, that is matrices. But obviously the basic of matrices, something like the definition of matrices and different kinds of matrices, you already have studied in your 10+2 level. So these are the basic concepts of 10+2 level. We are not interested about that things because the questions are asked basically for this competitive exam like IIT JAM, JEST, NEET, GATE, obviously from the eigenvalues and the eigenvector. So we will start from the topic of eigenvalues and eigenvectors. Okay, so let me tell you about something. Eigenvalues and eigenvectors, obviously, and eigenvectors. Okay, now when you talk about eigenvalues and eigenvectors, then obviously we have to deal with square matrices. So we will obviously deal with square matrices, and that is obviously, let me take as n cross n square matrices. Suppose we have a square matrices A, and if this A operate on a vector x, then what we will get? We will get obviously a vector in the right hand side. If a matrix operate on a vector x, then we will get a vector in the right hand side. But here we are interested about that vectors which are lying along x. So let me take an example that you can understand the thing better. So let me take a line which is passing through the origin, and this is, suppose this is the x direction, and a vector A is along this line. Now if you have a projection vector, projection operator P, that is obviously A transpose A divided by A transpose is the projection operator P, then if you operate on x, then you will get x obviously. But if you have x along this direction, that is perpendicular to A or perpendicular to this line, if x is along this direction, and if you operate now in this time on x, then you will get 0. So in general, if there is a vector which operate on x, you will get always x with some coefficient lambda, and here lambda is scalar obviously, and this is known as eigenvalue. So here this x is known as eigenvector, corresponding to which this lambda is known as eigenvalues. Eigenvalue, and you can see from here. So here is 1 into x and here is 0 into x. So the eigenvalue is 1 and 0, and this is obvious because it is P. This is obviously square matrix. This is obviously square matrix. So if this is square matrix, then you know that your p square minus p is equal to 0, because p square is equal to p. So in that case you have p into p minus I is equal to 0. So obviously you will get 0 and 1 eigenvalue. Okay, so this is actually concept of eigenvalue and eigenvector. So if you have a matrix which operate on eigenvector x, then you will get lambda times x, and this scalar lambda is called the eigenvalue, and this is eigenvector corresponding to this operator A. This is here the matrix operator A. Okay, now let me tell you some property of this equation or of this eigenvalue and the eigenvector. Okay, so suppose instead of A, suppose you have a square. So this is your main equation, Ax is equal to lambda x. Now suppose we have, instead of A we have a square. So if you have a square, x, and you can write it in this way also, that a into x, and now this x is nothing but lambda x, so this is a into lambda x. Okay, now again if you write it in this way also, lambda into x, then this x is again lambda x, then you will get lambda square x. So this is capital X, just lambda square x. So you can see, if x is the eigenvector corresponding to a, then x is also the eigenvector corresponding to a square. But here in this case the eigenvalue is lambda square, because you can see from here that this is a square x is equal to lambda square x. So if your x is the eigenvector corresponding to the operator a, then this is also the eigenvector of a square with eigenvalue lambda square, but here with eigenvalue lambda. Similarly, you can write that if you have a cube x, that will also be equal to lambda cube x, and in general you can write a to the power nx, that is nothing but lambda to the power nx. So this is one of the property of your eigenvector and eigenvalue. Okay, that if x is the eigenvector of the matrix A, then this is also the eigenvector of a square a cube and a to the power n with eigenvalue lambda to the power n. Okay, similarly another more interesting property is that not only the a square is a square a cube a to the power n, but this x is the eigenvector of a inverse also. How you can prove this? That this is not only the eigenvector of a square a cube, but this is also the eigenvector of a inverse. So if you multiply this equation with a inverse, you will get just a inverse ax is equal to lambda times a inverse x, and you know this a inverse is equal to x, so x is nothing but lambda into a inverse x. So your a inverse x will be 1 upon lambda times x. So now you can find from here that this x is the eigenvector of a inverse also with eigenvalue 1 by lambda. So we have got two property from here. One is, if x is the eigenvector of a, then x is also the eigenvector of a square a cube with eigenvalue lambda square lambda cube, and this is also the eigenvector of a inverse with eigenvalue 1 upon lambda. So these are very important property when we will solve problems. So please keep in mind these two important properties. Now the big deal is that how you can find out this eigenvalue and the corresponding eigenvector. So let me tell you what is the procedure of finding out the eigenvalues corresponding to eigenvector. So we can rearrange this equation in this form, that is ax minus lambda x equal to 0, that means a minus lambda I into x is equal to 0. But x obviously not equal to 0. So obviously this a minus lambda I, if this x is not equal to 0, then this a minus lambda I must be singular. This must be singular. And if this is singular, then the determinant of this, that means a minus lambda I is equal to 0. And this is your characteristic equation. This is your characteristic equations of this equation. So this is your characteristics equation. Characteristics equation. And the roots of this equation will give you the eigenvalues. So if you solve this equation, you will get something like lambda 1, lambda 2, this, and these are the eigenvalues. These are the roots of this equation, and these are the eigenvalues. So, and you can find out the eigenvector also corresponding to this eigenvalue. So if you want to find out the eigenvector corresponding to lambda 1, that is x1, so you have to solve this equation just. So if you solve this equation, you will get x1 corresponding to lambda 1. Similarly, if you want to find out the eigenvectors corresponding to lambda 2, then you have to solve this equation and you will get the eigenvector corresponding to lambda 2. So this is how you can find out the eigenvector and the eigenvalues corresponding to some eigenvector. Okay, and in the next class we will solve some problems so that you can understand this better. But before that, let me tell you some more properties of this eigenvalues. Most important properties about this eigenvalues. Okay, so let me take a 2 by 2 square matrix that will help us understanding very well. Okay, so let me take a 2 by 2 square matrix, something like this, A, B, C, D. So suppose this is our square matrix. Now for this square matrix, let me find out the eigenvalues. So what will be your eigenvalues? So if you write this A minus lambda I equal to 0 from here, so what you can write from here is that A minus lambda, B, C and D minus lambda determinant equal to 0. And now if you solve it, you will get A minus lambda into D minus lambda minus BC equal to 0. Now if you rearrange this equation, you will get this lambda square minus A plus D into lambda plus AD minus BC equal to 0. So this is your characteristics equation. And now if you solve this equation, you will get two roots of this equation because this is the quadratic equation. So if you solve it, you will get lambda 1 and lambda 2. So these are the roots of this equation. Roots of this equation. So the roots of this equation are lambda 1 and lambda 2. And if you observe, let me suppose that lambda and lambda 2 are the roots of this equation, and if you observe this equation, you can see that the sum of these roots, that is lambda 1 plus lambda 2, is nothing but A plus D. Similarly, if you find out the product of this root, that is lambda 1 lambda 2, that is nothing but AD minus BC. Now what this lambda 1 plus lambda 2 are? This is the sum of the eigenvalues. So you can write this lambda 1 and lambda 2 as sum of the eigenvalues. And you can see the sum of these eigenvalues are nothing but the trace of the matrices. So trace of the matrix. So this is nothing but the trace of the matrix. Trace of the matrix. Okay. Similarly, if you see here, this lambda 1, lambda 2, this is nothing but the AD minus BC. This is the product of eigenvalues, and this AD minus BC is the determinant of these matrices. AD minus BC, you can see. So this is nothing but product of eigenvalues is equal to the determinant of the matrix. So if you take this as a matrix A, then you can write this is determinant of A. This is trace of the matrix A. And please keep in mind that these two results are not only valid for this 2 by 2 matrix, but these two results are valid for any n by n square matrix. N by n square matrix. Okay, so please keep in mind these two important results that will help you when you solve problems involving eigenvalues and eigenvectors. Okay, thank you.